Okay, this will be an overview of the different features in the PointXP windows that are available. So of course through Celestron PWI you do show pointing model to bring up the main PointXP window here, which will show the currently loaded model. If you're building a pointing model, you can have this window up, and as you add points you'll see new points appear in the model. But for this demonstration I'll open an existing model. This one happened to be taken with a different mount, but it's got 37 points in it, and so there's some more interesting stuff we can show with this. So just kind of working our way from the top down, the axis alignment error is roughly the polar alignment error in an equatorial scope, or it's the zenith, the tilt relative to zenith for an Altaz telescope. The cal points over here, we have 37 active points out of a total of 37, and we'll get to active and inactive points in a moment. The sensitivity number is a little difficult to explain, but basically lower sensitivity is better. It means you can be more confident that the fit to the model is actually physically valid. So if you tried to fit 5 terms to 5 points, that would be a very sensitive model potentially, because kind of a small change in any one of those points could dramatically alter the terms that you've solved for. But if you've got 100 points and you're fitting a 5-term model to it, then that probably would have very low sensitivity, because adding the 101st point isn't likely to change your model significantly. Graph type, you can show the pointing errors, which is what's selected right now, or you can show the positions in the sky where those points were mapped. And so this is sort of like the sky view over here, except that it's just saying that there was a point mapped here, 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 kind of in this swath of the sky. And we can scale the graph using all of the points, or just the selected or just the active points, so we'll get back to that in just a minute. And down, so the main display normally is showing a scatter plot, showing after you have fit a model to the points that you've inserted, these are the residuals essentially. So if you were to go back and re-observe the exact points that you had observed while building the model, and let's suppose you already had that model in place, this is what the pointing errors would have looked like. So in this case, everything kind of falls within this 5 arcsecond circle. Down here, the reported pointing errors, the root mean square of all of your pointing errors is 2.6 arcseconds. This is kind of like standard deviation, if is another way you could describe it. And the point that is farthest out is 5.4 arcseconds. It's this point right here that's just outside this 5 arcsecond circle. Now there are a few additional displays we can look at. So there's error graph, which you can also get to through view error graphs. There's model terms, which you can also get to through view model terms. And the calibration point list, which you can also get to through view calibration points. And then there are 2 other less important screens here, which I'll just briefly mention to get them out of the way. The scale factor optimization wouldn't be relevant for Celestron mounts. This is where you have, when building the model, you pre-assume that you know the exact number of encoder counts per revolution. So in the case of the Celestron mount, it's 2 to the 24 counts per revolution. You kind of know that ahead of time. But for some mounts, like if you have a some gear reduction and you're just you don't necessarily know the exact number of counts per revolution, you start by guessing something close, and then this will go through and it'll try to scale the numbers to give you the best model afterwards. You have to optimize that number in a different way, and it's a little more computationally intensive. So that can be done through this screen, but rarely needs to be done in the case of something like a Celestron mount. Settings is just informational. It gives you the latitude, the temperature and pressure that's being used to calculate refraction in the model. Even if these are wrong, any error in the refraction calculation basically gets absorbed into the main model terms. So these just kind of provide a baseline amount of refraction calculation, and then the rest kind of gets absorbed into the rest of the model. This also shows the mount type that the model was built for. In this case, I loaded a model from an Altaz telescope. And then these are just the encoder counts per revolution, which we've normalized to just be 2 pi radians per revolution. We kind of go from raw encoder counts into radians when inserting into the model. So that's where these numbers come from. Now, coming back to the other screens, I think the first interesting one to look at is the calibration point list. This is just a list of every point that's been added to the model. We can go through the list, and if you select a point, you see that corresponding point highlighted on each of these graphs. So, for example, I can switch over to the positions view, and as I scroll down, I can see the order in which these were mapped. You can tell that this was done with an automated sequence that was kind of sweeping around in azimuth. We'll go back to the errors view, and so the list gives us, of course, the number of the point as it was inserted, the time when that point was recorded, the right ascension and declination at the moment the point was mapped. This is where the telescope was actually pointing based on the results of your the plate solve of your image, or by telling it that, you know, I am pointing at Arcturus. These would be the RA index of Arcturus in that case. Theta and phi are the internal mount coordinates. Theta is roughly the declination axis for an equatorial telescope, and phi is roughly the right ascension axis in an equatorial telescope. Or for Altaz, this would be altitude and azimuth, roughly. Theta and phi are kind of the conventional characters, Greek characters used in spherical coordinate systems. So that's where those terms come up. PointXP internally is treating these as just generic spherical coordinates, and so that's why those terms are used. The error here is the residual error after the model has been fit to all the data. You go back and you subtract this actual measurement from the model's prediction of where that point would be based on the best fit, and in this case it was 5.4 arc seconds of total distance. That's broken down further in the RA error and DEC error columns. So you can see, for example, if everything is shifted by 20 arc seconds in RA, then that might tell you that you've got a clock problem. Your clock is off by 20 arc seconds. And then the use column just tells you which of these points are actually contributing to the fit of the model. So you can say we want to remove this point here, which is kind of the farthest out outlier. We don't have any real outliers in this scatter plot, but let's say we wanted to remove that one, or at least not allow it to contribute to the fit of the model. We can disable it in a few ways. One way is we can just click on it in the scatter plot, and that turns the point red, and it now shows up as being not used. Another way is we can just double click this row to toggle it. And yet another way is we can just select one or more points. You can do the normal kind of shift select or control select to select multiple points, and just hit disable selected, or control D is the shortcut to do that, and disable those points. So let's say that there was a point that you knew that, you thought you were on one star, but you were actually pointing at a nearby bright star that wasn't really the correct star when you actually mapped the point. After you got 5 or 6 points, that one is going to show up as an outlier, so you can go back and disable it. Or another place where you might use this is if you are polar aligning and you build a 4-point model. You do the trick of rotating all the points to let you do an all-sky polar align. You align, and now the model is still usable now that you've aligned, but it may not be fully accurate. So you can go back and add another 4 or 5 points, and then go back and disable or delete those original 4 points from the pre-polar alignment state. So as we disable points here, let's just go ahead and disable everything. And you can see that our errors are enormous now because we're fitting basically a 0 model. And these are just the raw errors exactly as they came off the telescope. So if we had gone through and tried to point the telescope without any pointing model, these would have been our pointing errors. And as I start enabling points, we can watch what happens over here in the model terms window. So these are the terms that go into a large polynomial, essentially. Well, not quite, but anyway, a large mathematical equation. You plug these numbers in and you get a function where you put in where you want to be pointing, and you get out where the encoders would have to be pointing at that position. And with no points in the model, we get no terms. And then as I enable the first point, we get encoder offsets. And when I enable the second, or maybe the third point, maybe the fourth point, because these were all clustered pretty close in the sky, now we start to get our polar alignment or zenith misalignment terms and our cone and hub terms. And one little trick, I always forget which one is cone, which one's hub, so I added tooltips to tell you that cone is the optical axis and deck axis non-perpendicularity, and hub is the RA axis to deck axis non-perpendicularity. So as you map more and more points, you are able to fit more and more terms. And coming back to the sensitivity number, what you typically find is that when you're solving, we have 3 points, and we're only fitting encoder offsets to that right now, but our sensitivity is very low, meaning that a 4th point wouldn't likely affect the offsets very much. But as soon as we are able to fit more terms, our sensitivity initially goes up because we're now fitting 4 calibration points, which is really 8 pieces of data because you have 2 coordinates per point. We're fitting 8 pieces of data using 6 terms, and so our sensitivity goes high. And then usually as you add more and more points, your sensitivity drops and continues dropping, and when it gets low enough, that's when it can kind of start to press onward and fit more terms. So this is sort of the pattern you see, is you kind of start populating left to right along this top row as you add more points, and then you start filling in more of these higher order terms. And we can also come back to a few things I mentioned earlier, where the calibration points, you can see that only 10 out of 37 available points are actually active. We can scale this graph. You see we have the scale of the graph shows a lot of these outliers that haven't been activated yet. If we want to kind of zoom in just on the active points, you hit selected points and it shows those. So that's what that is doing. And here I'll just point out that we have information about the RMS of all of our data points. So all the points, including the ones that aren't contributing to the fit of the model, have an RMS of 20 arc seconds, and just the active points have an RMS of 2.2 arc seconds. Now let's go back and re-enable everything. And you can see with the large model we get this set of terms. It only tries to fit terms that are enabled using these checkboxes. So let's say that we didn't want to fit for cone or hub for some reason. We could turn those off. You almost never want to do that. So in practice, if you click recommended for equatorial, it will enable the terms that are most likely to be relevant to an equatorial mount. And if you click recommended for Altaz, it'll enable just the terms that are most likely to be useful for an Altaz telescope. And that happens automatically when you connect to a CGX mount. It will automatically enable the recommended equatorial terms. You can also enable or disable all, but sometimes it will solve for a term that then bumps the sensitivity high enough that it can't solve for other terms that may actually be more relevant. So I would almost always just use the recommended terms, unless you're experimenting. So now we can come over to the graphical error analysis. All this is we have our scatter plot up here, but sometimes if you're trying to learn something about your mount or look for interesting behaviors, it can be useful to graph this data in different ways. So again, theta is declination and phi is right ascension, more or less. So we can just select, I want to plot the declination versus the error in declination. Or this data was taken on an Altaz mount, so really I'm plotting altitude versus error in altitude. And in this particular mount, there actually is maybe a tiny amount of sinusoidal structure in here that, maybe could be worth going back and programming in another term to compensate for that, but it was very small amplitude, kind of 2 arc seconds of amplitude. So we can also go back and do, let's look if there's any error in phi that is dependent on theta. So error in right ascension dependent on declination. You can explicitly look for RA and dec error, which in the case of an equatorial mount, error in RA will basically look the same as error in phi, and error in dec will basically look the same as error in theta. Similarly, for an Altaz mount, error in altitude will basically look like error in theta. Error in azimuth will basically look like error in phi. The x-axis here, you can do theta, phi, zenith distance is sometimes useful. Time will kind of help you, especially if you're trying to figure out, I took 4 points early in the night, and then I polar aligned, and then I added more points later. This just makes it really obvious that there's one cluster of points early in the night and then one cluster of points later in the night. So it helps you disable those as needed. Again, in this graph, you can click to enable or disable a point. And then finally, point number just orders them sequentially as they were taken. And interesting things you could see here in a large model is if you've got clock drift, you might see kind of drift in RA over time. So I think that just about covers everything, about opening and saving models. So if you go in, if you build a model and then you disable 2 of the points and then you save it, then it will save not only the data, but also the fact that 2 of those points have been disabled. And so when you go back and reload it next time, those points will still be available, but not contributing to the fit.